Okay, welcome. The background about PSS on cable failures is the high number of CPS failures observed. And this is around the accelerated water particles around foundations. And the insurance industry requirement the CPS to be stabilized, which is predominantly around a specific CPS designed hypermobility on the seabed. Of the lesser known things is the extent of these accelerations and the extent these accelerations actually have on the erosions around the foundations, both on monopiles and global scouring around both monopiles and jackets. As you can see in the illustration here on the right-hand side, you see these horseshoe vortices that is actually rolling horseshoe vortices that is being driven by the waves around the foundations. If we go to next, Ole. Why are we developing the PSS? The current CPS offerings do not solve the cable fatigue and failure issues, and the insurers require the CPS stabilization. When we've conducted analysis with CFD with SST turbulence assessment of wind parks mid-ocean data, we have actually shown that the actual water particle velocities are accelerated up to 4 to 5 times the actual or the higher than the initial estimates, so that the cables and CPSs are basically analyzed at 4 to 5 times lower forces than is the actual, and therefore underestimating the CPS and cable fatigue life. The CPS systems that can be managed from a cable lay vessel and installed into a foundation cannot be of such stiffness that it can prevent the CPS from moving around beyond the touchdown point on the seabed or on the scar protection to be stable enough that it won't move on the seabed. And that's the reason for that. You cannot really intend to build a CPS system that can do this. And this is the reason why we developed the solution of the Portunus stabilization system. Next. The key features and requirements for the effective CPS stabilization is obviously the stabilization of the PSS into the seabed and the bend stiffening. It's also that we can provide immediate seabed stabilization, immediate meaning that right after the device is actually placed over the cable protection system, that it's actually stabilized into the seabed, and that we can provide adequate fatigue life for the cable and CPS under realistic conditions, and that we can use this both on existing infrastructure, so for brownfield, and we can use it for new greenfield projects, and that we can do this from remotely operated installation. So this can be done from surface vessels via RV installation. Next. So this Portunus stabilization system is designed to be installable on all kinds of seabed. So both we can do it on seabed of predominantly from sandy seabeds and all kind of loose seabeds, sediments. So like in the Taiwan Strait and in the North Sea, where you have various kind of sand, they differs. And of course also where we have monopiles, where we would have scar protection as shown on the right hand side. Here we say we write retrofit. The system is designed so that the PSS will actually be installed either right after the CPS is pulled into the foundation or anytime thereafter. So it can be retrofitted, it can be fitted right after the cable protection system is latched into the foundation during an installation, so for a new project, or any time after that. So retrofit can be obviously any number of years after it has been installed. Next. So how does the PSS prevent the premature CPS failures and cable and CPS failures? Because it distributes the bending moments between the foundation and the seabed interfaces. So the PSS provides the seabed end of the cable protection system with a bend stiffening, so a cable bending strain relief onto the leading into the where we actually pin the PSS into the seabed. So where it's pinned into the seabed, it actually leads into this pinpoint over the length of the flexible bend stiffener. So there we provide the cable with and the cable protection system with a bend stiffening curvature. We do this. We by using the screw piles, we provide instant stabilization, and we actually get the anchoring by use of these foundation piles. And as we said before, we can do this with remotely operated vehicles, and we show here the two pictures. Here we have on the top, we have the scoured seabed around both the foundation and the actual PSS structure, and on the bottom here we just show the curvature of the PSS when the CPS is being in one of the extreme frictions from the wave, when it's been cyclic move from here at one extreme side, and on the rear side of the same wave will be taken to the other side. Next. So installation and the screw pile of so installation and of the PSS and the screw pile mechanism is, again, as we said, with RV and the screw piles that we actually screw into the seabed is here shown at the mid picture here, where we use screw piles that screw into the either sandy or at least a seabed that we can screw these into. Where we have scar protection, we actually use a casing. So we drill through first the scar protection with a casing, and then we actually drill the screw pile through the actual this casing into the seabed beneath the scar protection. This allows us to still, through scar protection, provide a quick commissioning, and later at decommissioning, we can equally provide a quick decommissioning time. We can achieve more than, or we will achieve more than 25 tons of anchoring strength for each of the screw piles that we use, and also that we get immediately the anchoring strength validation. This we provide via a cloud-based system. So on board, on the vessel control room, one will have the data on the actual validated anchoring strength of the screw pile during the screw pile operation. Next. So the advantages of the PSS application is that the bending strain relief provides the cable with the reliable fatigue life. The screw piles that provides the PSS with the stabilization, and the compact system design allows for an easy storage and handling on board the vessel, operational flexibility, both in terms of that it's handleable and storeable on board the vessels, operational flexibility, reduced operational risk in terms of that there's no surface vessel operational operation in proximity of the actual foundations offshore. Next. The added benefits of the PSS application is that it's cost effective. There's both less ecological and impact versus rock dumping, and also there's a full separation, 100% separation of the actual foundation, the foundation of the actual VTG foundations and the cable campaign. So there's no post cable campaign rock dumping by use of the PSS. And the stabilization obviously comes with the verified anchoring strength. So there's no uncertainty. So you don't have any dependence on whether what kind of strength you actually achieve in the seabed, what kind of seabed you have from the CPT or whatever surveys that's been made. You actually get the validated anchoring strength from the screw pile operation. And also with any kind of future uncertainty in terms of the seabed mobility from after the installation, the raise and drop, ripples, sand waves, whatever, those limits can be incorporated in the design. And of course, the end of life benefit is first of all that the curvature control ensures that the cable fatigue and similarly the CPS fatigue life exceeds the wind farm project life, and that the foundation piles and PSS can be fully recovered and of course then also recycled and decommissioned. So after decommission, there's nothing left at the seabed. Everything is fully recovered and removed and can be recycled onshore. Next. So in comparison with rock ballast, the PSS is a new solution. It's instant stabilization from vessel, whether that's from the cable support vessel or whether it's from ROV support vessel. It's more cost efficient, no rock impact risk from the installation. There's a bending, strain, relief, curvature, and it adapts to all seabed changes. And obviously the CPS catenary or trajectory remains, and it's a quick and full recovery system. So in comparison with the ballast or rock dumping, which by some of the developers is referred to as Band-Aid solution, which of course, where the armor layer of the scour protection can act as the stabilization of the CPS, but the rock ballast stabilization is more costly than the PSS, and the impact load may affect both CPS and the cable. There's no separation between the free part of and the pinned down part of the cable and the CPS. So there's no coil spring model in it, and that's where the fatigue is obviously critical in this solution for the cable particularly. And there's a higher environmental impact of this solution compared to the PSS. Next. So overall, it's a cost-effective solution. It stabilizes with bend stiffener at the seabed interface. It's independent of seabed and or the installation interfaces. It has minimal ecological and environmental impacts. It supports also local production, so we can have both local and regional supply chain. It maximizes the cable lifetime, and it minimizes the chances for cable repair or need for cable repair and maintenance. And of course, it enhances the transmission safety. Next.